Cool. Welcome, everybody. I'm going to talk to you today about Wavefront, and standard disclaimer slide first. I'm actually planning, the good news is everything I'm planning to show you is things that you can try out today. We actually just launched our first self-serve trial yesterday, so you can go to wavefront.com, sign up there, and try any of this stuff. I will keep this disclaimer here in case I get questions that go into futures, but everything that's planned for this is current Wavefront. Here's what we're going to be covering. First of all, I assume that for most people in the audience, Wavefront is new to you. Is there anyone here that is already familiar with Wavefront? All right, perfect. So we'll look a little bit first at just what is Wavefront, get you situated with the product. Then we'll move into kind of the data science part of this talk. We'll look at what do we mean by smart alerts and how you can do smart alerting by detecting metrics anomalies. And in the final piece, we'll give a framework for how you can actually think about anomalies and how you can think about detecting them. Wavefront is a recent acquisition by VMware. I come from the Wavefront acquisition. I was one of the early employees there, and I've done a number of different roles at the company, including leading the sales engineering team. So I've worked with a lot of our customers. In fact, most of the current Wavefront customers, I've worked with them as they've started to use the product. At this conference, VMware has also announced a whole raft of cloud services, and Wavefront is a piece of it. So this talk is going to focus on Wavefront, but there are other cloud services that you can learn about here at the show. Let's get into the introduction. So this is actually what was on our original website, the original definition description of what Wavefront is. And the title of this talk is The Wavefront Story, so I'll give just a little bit of context of where Wavefront came from. Actually, some of the Wavefront founders happen to be sitting in the room here, so they could probably tell this story much better than I can. But Wavefront is essentially a hosted platform for ingesting, storing, visualizing, and alerting on metrics. And we'll be looking in a lot of detail at what we actually mean by metrics and what you can use Wavefront for. But where it came from was the founders of the company were working at places like Google, Twitter. Those companies had realized as they started to basically build very complex architectures on top of containers, microservices, etc., that traditional ways of monitoring those environments were starting to break down. There's just too much change, too much ephemerality, and traditional tools just can't scale to that level to deal with it, and they can't look at the relationships between all that changing data to make sense of what's going on. Now, those companies like Google and Twitter and others, Facebook did this too, they all built systems somewhat like Wavefront internally. That's what they used to monitor inside those companies, but they didn't release them externally. So what Wavefront was the goal was take those technologies that those companies built and bring them to mass market. And that's what Wavefront is. So it's all about metrics, right? And what are metrics? Actually really simple. Metrics are just any numeric value that changes over time. And there's metrics everywhere in the world. Just temperatures, speedometers, all just metrics everywhere. Of course, Wavefront's customers are using the system to monitor technical metrics about the behavior of their applications, the behavior of their infrastructure, behavior of their network, their storage, things like that. But effectively what Wavefront is a system that lets you work with ingest any metric and then analyze it, query it, alert over it. And we have a picture here of a thermostat. People at VMware, since we came on board, have written blog posts about how they got their Nest thermostat data into Wavefront in a couple of hours. So it's actually really easy to get any kind of metric data into the system. And why metrics? It comes down to speed and cost. So traditionally, this kind of stuff that I'm going to show you has been done with log systems. VMware has Log Insight, but there's Elk, Stack, Splunk. There's a lot of log systems out there. The big difference between logs and metrics is metrics are just the numeric values. So they're way easier to parse than logs. You can directly compute things on top of them. Usually what a log system basically does is parse out metrics from the logs and then start doing computation on top of that, which is quite slow and quite expensive, both in terms of storage and just actual query performance. And we'll see that as we get into Wavefront here. Here's what data looks like in Wavefront. And I'm kind of contrasting here between a metric and a log line. It's very similar data here in the metric format and the log format. You see you have a metric name. In this case, it's measuring the number of successful response codes we've gotten from Apache. The current number that we've had since we started reporting it. So since we started collecting this data, we've had around 25,000 successful requests. The timestamp when it happened. This is just Unix epoch seconds, so we don't really care what time zone the data is coming from. Where the data came from, so we always have one tag that just says what's emitting this data. Very often that's a host name, could be a VM, it could be even something else like a stock ticker symbol, just where is this measurement coming from. And then you can give other key value pairs or dimensions to categorize or tag this data. In this case, the port that this service is listening on, and the endpoint that we're measuring the successful counts for here. So much shorter and simpler than the fairly complex log line that you see below it. And then this is what Wavefront is. It is a hosted platform, as I said, that provides everything you need to work with that kind of data. We allow you to ingest it at really high scale. We allow you to query it, visualize it, alert over it. We manage it for you, so we deal with all the scaling problems of how can you send or measure everything from across your environment if you're a large organization. And we're used by multiple people within the enterprise, right? So SREs, developers, operations folks. Within our customer base, so the customers we have today are large companies like Box, Workday, Lyft, Groupon, Microsoft. We have hundreds, and in some cases, thousands of users at those customers across these roles that are using Wavefront on a daily basis to monitor everything that's going on with their stack. How to get data in, right? So in order, the first step to this is send metrics into the system. There's basically 4 ways of doing it. And for the most part, it goes through something we call the proxy. So the Wavefront proxy is a small, actually open source component that we ship. It's basically a buffer point between your systems and the Wavefront service. So Wavefront is a SaaS offering, and no one wants a SaaS offering to call out behind their firewall to pull data out of it. So the proxy is what gives us this push model. You send metrics to it, it buffers those metrics locally. So if for some reason the metrics couldn't be sent, they'd queue up locally, and whenever the network issue was resolved, the data would flow, right? So you never lose any data. And there's basically 3 common things that people send to it. One is just use agents. So Wavefront ships with a really nice agent for collecting data from your infrastructure and from common applications that you might be using. There was an example of Apache a couple of slides back, but common databases, et cetera, et cetera. The next is via logs themselves. So most people have a ton of log data today, and it's fairly straightforward, although it takes a little tuning to parse the data out of those logs into metrics. And the proxy has a feature for doing that. Most of our customers are also instrumenting their code itself. So they're measuring not just their infrastructure and the common applications they rely on, but the behavior of their actual code. And from that comes their business KPIs as well. So I mentioned Lyft is a customer. They actually measure in Wavefront, as well as all the technical metrics like the number of completed rides, number of canceled rides going on every minute across all the geographies that they support. And all of those business KPIs come out of this code instrumentation that they do. And in fact, for this show, we should have updated this we have one more. So For cloud services, if you're either running on a cloud or you've got some of your infrastructure running on cloud, you don't even need a proxy, right? Wavefront is a cloud service. Amazon is a cloud service. We can just pull your data from Amazon directly into Wavefront without needing a proxy. And we have just added Google to this external kind of integration as well. The key to all this is that everything that Wavefront does on the front end is just calling APIs. All of those APIs are nicely documented, clean, and you can integrate any of your stuff with Wavefront. So most of our customers do use the Wavefront UI, but you could actually automate and integrate around it however you like. And so we make it very easy to get data in and get data out of the system. And these are the things that really make Wavefront stand out. Most of these I hope you'll see in a demo in a second here. The first is just amazing scale at which we can ingest data. So our largest customer today in terms of data rate is Box. Box is sending into Wavefront right now about 600,000 metrics per second. That's billions of measurements every day. We keep that data around indefinitely. We never roll it up. Most systems like this will start to summarize data over time to save on storage costs. Because of the way we work, we don't need to do that. We keep the data indefinitely. While Box is ingesting about 600,000 metrics per second, they're actually querying out about 4 million per second. So they're actually reading the data out even faster than they're sending it in. We really enable real-time investigation of your data in an ad hoc way really nicely, and you'll see that in one of the demos that I'm going to show. Because of the query language that underpins everything that Wavefront does, we can do really complex analysis of your data, do correlation across your entire stack, and answer really difficult questions about your environment that maybe you never had a way of actually asking or getting the answer to before. And then a big focus of this talk is going to be around alerting. And Wavefront enables you to get far beyond the traditional kind of threshold-based alerts that you may be used to today. And if I can get this to work, I'm going to hop over to a demo. I might need some backup to get this to flip. I must have pressed something that caused the black box to come up. Okay, and then try 5. All right, here we go. Cool. All right, so I'll just start here. Your first landing spot in Wavefront is something like this. So say you were to start a trial today, you would get presented with a whole bunch of integrations to make it easy to get started with Wavefront. So I showed that data format earlier, really simple format. And because it's so simple, even if there's stuff you want to work with that's not here, it's generally very easy to get that data in. But there's a whole bunch that comes out of the box. I'm not sure if there's any Pivotal users here. Couple. So Pivotal is one that we did recently. Just to show you how this works in general, click a button in the integrations page. You'll get an overview of what this integration is going to do for you. Simple setup instructions for how to get going. Some diagnostics of whether it's basically working. And a whole bunch of dashboards. So for Pivotal here, there are 12 dashboards that come out of the box. And if I drill into one of them, you'll see how fast you can start working and graphing and looking at your data. This is kind of like an overall health summary of the Pivotal environment here. I'll show a little bit about how dashboards work in Wavefront in general. Now, one of the differentiators that I pointed out was our ability to do ad hoc investigation of data. I actually think that's more unique about Wavefront than dashboards. Everything's got dashboards, right? Wavefront happens to have very pretty, very fast ones with some nice features that I'll show you. What you'll also see in a little bit is the ability for Wavefront individual charts that drive these dashboards to allow you to ask on-the-fly questions really easily. And the contrast on the projector is not great, so I might actually switch to our dark theme here. Hopefully it'll pop out a little more then. All right, cool. So I wanted the dark theme to highlight here these events on the data. So as I've said, Wavefront is a system that lets you ingest any numeric value that varies over time. And this dashboard is fairly representative of the kinds of things that our customers use the system for. They're measuring data from their applications, database, basic infrastructure stuff like CPU, processors, memory, from their storage, from their network, everything all together in one place. As I scroll through this dashboard, you'll see various different chart types that we support, big number widgets, stacked area charts, and so on. And we have highlighted here an event. So mostly the kind of data that we work with is metrics, but you can ingest events too, which can really give you context into why the metrics are behaving the way they are. And in this case, we've marked where we did a deployment. And it actually looks like there was a bad deployment here. Like many of these charts, the data looks kind of weird, right? If I click and drag to zoom in, you'll see there's no static images in Wavefront. It's all very dynamic. I can easily push that time period out to all the other charts. So now I've synced this dashboard on the time slice that we're looking at. One other thing that I'll highlight here is as I hover over the legend, and it shows me the values of what's going on at that point in time, you'll notice that the line that I'm focused on is highlighted and the others get diminished. If I click that line, it'll actually highlight that same thing on all the other graphs. So if you see something of interest, you can click it and see across the whole dashboard what's going on very easily. Anytime that you're looking at data in Wavefront, we make it very easy to share that with others. So I just grabbed a short link to this dashboard. And if I pull it up, say I sent this to a colleague, or maybe I actually put this in an incident report. Like this looked like it was a bad deployment, right? Maybe we do an incident report about that bad deploy. If I stick this link into the incident report, it's going to persist exactly what I wanted to see indefinitely, forever. And I didn't highlight it until just now, but if you look at the top of the dashboard, this is actually data from back in 2015. So this again speaks to the fact that we keep the data that you ingest into our system indefinitely. Most systems, if you stuck a link into it for an incident that happened in 2015, and then you looked at that incident again in 2017, like we have this another bad deploy, it looks very similar to what we saw last time. Most systems would have rolled up or summarized away all of this data. Wavefront doesn't do that. And of course, it's very easy to look at it live. So if I just click the live button, I'll remove this highlight here. I'm now looking at this same dashboard live over the past 2 hours. And you get a sense for the speed of the system here. I just put this dashboard into live data over the past 1 week, and it just loads in almost as fast as the 2-hour chart did. And this is over just the conference Wi-Fi, by the way. So I'll show a couple of quick examples. Behind every chart on a dashboard is an individual chart like this, which has queries driving the questions that that dashboard is answering, right? And we talked a little bit about iterative exploration of data. And this is a little example showing how that can work. The idea here is, again, we've marked where we made a code change. We're just looking at CPU load here across a bunch of systems. And where we did the code change, you can see that we had looks like a spike in CPU. So it looks like this change led to an increase in CPU load. But it's very noisy, right? Spiking up and down. If I went to the team that did this code push and said, it looks like you made CPU load worse, it kind of looks like it went up. That's really vague, right? They're probably going to push back and say, show me some more evidence. So we can use Wavefront to get a more precise answer to this. First thing I'm going to do is use our query builder here It nicely helps you explore the different functions that are available in the language. And I'm just going to take an average of this data. Query Builder is nice because it gives you documentation of all the functions and even a live preview of what will happen if you apply that function to the data. And when I take the average here, it's taken all those machines that we're reporting, and it's just collapsed them down into a single line. And when I do that, it's even more obvious that right when we did this code change, CPU load jumped up quite a bit. The timing of this is enough that I might say the code deploy is the thing that caused this, but maybe it's a coincidence, right? Maybe there's some kind of backup event or something that happens every day around this time, and it just so happened to coincide with the code push today. We make it very easy, and I'm going to just type the language here instead of the query builder. We make it very easy to look at your data at any point in time. So I've just copied that previous query and named this one yesterday, and I've said lag this data by 1 day. This function is an example of a function that takes a time window argument. You can give it seconds, minutes, hours, days, weeks. So it's trivial to look at your data at any point in time. Here I just want to look at what happened today versus yesterday. But say I'm a retailer and my busy time of year is Black Friday. I might want to compare how are we doing this Black Friday versus last Black Friday. I just lag it by 52 weeks, and I see that, and I see it in seconds, right? When I look at this data, now this makes it clear that this is not a daily occurrence, right? The orange line is yesterday's behavior, and before the code deploy, yesterday and today, we had a very similar steady state, persisted through the night yesterday, but we jumped up today. And so now I'm very confident the code deploy is what made the change here. And then let's go back to the original idea here, which was, can we get a more precise answer into what actually happened? And that's really very easy as well. If I just divide today's CPU load by yesterday's CPU load, now I can see in a single line that as a result of that code deploy, our CPU load increased by about 35%. So now if I file a bug, I can include the link to this evidence, and I can say CPU load increased by 35%. Please take a look and see if we can get better, right? And I'm no longer giving the development team imprecise thing. I'm saying exactly what happened, and I have the evidence to back it up. And this also begs the question, by the way, which I'll show next. If I can detect that my CPU load jumped up by 35%, well, I might want to be alerted by stuff like that, right? I might not want to even have to do this kind of investigation. I might want the system to just tell me CPU load increased by more than 20%. You should take a look at it. So let's look at alerting next. I like to use this example for basically how alerting works, mostly because it came from a customer. So this came from a customer support ticket, the sort of the rough shape of the data. It's not exactly the same, but it's very similar. And this data was request rate into a front-end load balancer. And the most obvious thing about it is the spikes, right? The left-hand side of the chart has these big spikes. They look crazy. They look like an anomaly. They look bad. But actually, the customer didn't care about those. What the customer really cared about was this thing over here. So if you ignore the spikes for a second, you can see that the request rate over the middle of the night was a fairly steady, about 175,000 requests per second. As people started coming into work, the request rate started growing. It reached a peak at about 285,000 requests per second, but that peak could not be sustained for some reason. It dropped, and it dropped for about an hour, which was a serious outage that they wanted to catch. Now, the system that they were using for alerting prior to Wavefront, if you set it up to detect something this big, it would also fire over the spikes, which are so much bigger. And the beauty of having a query language like Wavefront has for alerting is that you can use the language to manipulate your data before you alert over it. You're no longer limited to alerting over just your raw data, right? And so the way we solved this problem was like this. Here we go. Maybe my network connection's going to give up on me. Yeah, that's right. It's moving median, and it should be returning. I'll try refreshing the whole thing. If anyone knows the speaker Wi-Fi password, that would be good. I think someone might have brought me a Ethernet that I can try too. Let's see if this picks up the network. All right, here we go. We're back. Wired network now. All right, so the orange line is the original data, and the blue line is that smooth data. And you caught that it was double M. It's moving median. So what it's doing basically is taking it's a moving median over a 10-minute window. So there's just this sliding window of the average data, the median data, across this chart. And when I do that, the spikes go away. If for those that don't remember their high school math, which was like me when I joined Wavefront, the way I like to think of this is and I'll show actually, if I do the moving average or the moving mean instead of the moving median, we can see that the spikes are not quite as smooth, right? They're still spiking up a little bit, but they're smooth somewhat. The way I like to think of it is, say this graph wasn't showing request rate. Say it was showing average net worth of people in a bar. If Bill Gates walks into the bar, the average net worth jumps up quite significantly. The small numbers of large deviations from normal drag the average up really fast. But if you're looking at the median, which is what works nicely here, when Bill Gates walks into the bar, the median net worth in the bar doesn't really change much at all, because the median is just the middle value. So one large deviation from the norm doesn't matter. And so now we can alert over this blue line, which is what the customer really considered their actual data to be, rather than the original noisy, spiky data, right? Now, Wavefront alerts work really simply. All you need to do is introduce Boolean comparisons to say what you want to catch, right? And in some cases, it could be really simple. Like if you just wanted to know, I never want memory to go below 500 megs, you could just write below 500 megs, and you're done. In this case, it's not so simple, because if I said, alert me when I go below, say, 260K, well, it's below 260K most of the time, so that alert would just be firing all the time. There's a couple of ways you could look at this, but I'll show you a pretty cool way. I'm actually going to plot the original data onto the other axes. I've pushed it onto the right-hand axis, so we can play with our alert condition a little bit on the left-hand axis. And what I'm going to do is just take that smooth data that we had and divide it by what it was doing 10 minutes previously. So now I've basically created a 10-minute sliding window of the percentage change in my request rate. And I can see that even though it was growing during the day, in any given 10 minutes, it never really changed all that much, by like a few percent here and there. But when the bad thing happened, it actually dropped off by more than 10%. So it dropped really fast. And now if I want to alert over that, I just say, I want to be notified whenever my request rate drops by 10% or more in 10 minutes. And that query is that easy to write, okay? I like this example because it's a more interesting example than very traditional threshold kind of alerting. Like we're looking for percentage changes instead of absolute changes. But at the same time, it's very simple. Like you can use this query language to do, and you'll see in the anomaly section in this talk, some complex uses of the query language to do things like standard deviation and things like that. But here it's just very simple. Tell me when my request rate drops by 10%. And of course, this will learn over time. If a year from now we've doubled our usual request rate, we still want to know if we have large percentage drops, right? So it's kind of a little bit of a self-tuning alert. Last thing I'll show you here is, let's do this on some live data. The way it works is, once you've set up your condition, you can create your alert just right there on the chart. So anytime you're looking at any data in the system and you see something interesting that you want to catch and know about in future, you can just create an alert from that. I'm going to do this with some live data and show you how it looks. So now I have just some request latency data here. I'm going to look at the moving max. How high did that request latency get over a 10-minute window? And I'm going to create an alert from this. And let's pick a value, greater than 240. Okay, so what's really cool about this is it's actually backtesting for us when this alert would fire based on the conditions that we've set up. Remember I showed you a dashboard earlier where there was an event that we'd overlaid? That was an example of a sort of a manual event, like we've integrated our build system with Wavefront to tell Wavefront whenever we're doing a build. Whenever a Wavefront alert fires, it will also create an event for the duration of that alert firing automatically for you. And it will automatically associate that event with the things that are causing it to fire. What that basically means is if you're looking at your data, you're looking at dashboards, charts, you're going to see appropriate alert overlays for the data you're looking at automatically without you having to do anything. And here it's showing us when the alert would fire. This is really cool because it takes a lot of the guesswork out of setting up alerts. Like most systems, you kind of have to think about what makes sense, run it for a couple of weeks, and then you just find out in practice, did it miss things that you care about, or did it fire for a whole bunch of stuff that you don't care about, right? With this, if you had, say, a bad incident last night, you can set up your alert, you can confirm that it would have caught last night's issue, and you can also confirm that it wouldn't fire over a whole bunch of stuff that you don't care about. So it takes a lot of the guesswork away. And then it's also very easy here to send these alert notifications wherever you want. Email addresses, PagerDuty, webhooks to integrate with basically anything, Slack, VictorOps, even to run automated remediation routines, perhaps. All right, so I'll come back and show some more demos as we go through. But this brings us in, so we've seen how alerting works, basically, and then this brings us to the topic of metrics anomalies and how to do alerting in general. Just going to level set a little bit first. If we're going to talk about smart alerts, we should probably think about what not so smart alerts look like. And they tend to be very simple thresholds or just simple status checks. Is this thing up or down? They tend to only look at univariate data, like one series. Like I'm looking at CPU on this one machine. Is it good or bad? And they tend to be all or nothing. Like either this alert fires and it goes to everybody in the organization, or it doesn't. And this leads to a few problems. The first, of course, is just too much noise. A lot of false positives and a lot of false negatives, leading to a lot of alert fatigue. You can't use relationships within the data. So the CPU is going high. That might be fine if the request rate is also spiking. Like you might expect the CPU to increase if request rate is spiking. And so you need a system that can combine metrics together like that to alert smarter. And there are just too many people involved. Like basically every problem goes to everybody and everyone is confused about what's going on. So if we could be smarter about alerts, we'd have a more expressive language to detect anomalies and only fire when there's a real problem. And you've seen a little bit of the Wavefront query language already. The ability to express relationships between data, as we've seen a little bit already, and also have a severity hierarchy with targeted escalation and self-service so that if I'm a developer and I'm writing code and my company is operating that code, I might want to know what is the behavior of my stuff in production and be able to do that for myself and both visualize it and be alerted over it myself without needing to get anyone else involved. And this leads to one of the interesting things that we've seen in our customer base, and I guess it really speaks to the DevOps movement in general. So what we've observed is that our customers, all those big companies we talked about, Intuit, Groupon, Box, etc., they've kind of stopped trying to scale up their ops teams to cover every eventuality. Like the systems that they're operating are getting so complex that scaling operations to understand everything and be on top of everything is very hard, right? Instead, they're scaling out to the development organization. So they're actually, these companies are operating the code that they write. It's not just like a shrink-wrapped software that they send off somewhere and they don't really have any concept of how the customer's actually using it. And so developers start to look at and alert over their own data. And they tend then to have these hierarchies of who gets alerted by what. The blue is developers doing their own alerts. Not really paging necessarily, just getting emailed about when interesting things are happening. There's a middle ground where both ops and development is involved, but it's still email-based. And then the red thing in the middle is severe things that are causing an issue right now that have to be investigated that will page the on-call team to look at in more detail, right? And there is a bit of a trade-off here, like the bigger you can make that blue box, the smaller you can make the red one, and the more focus you can get your operations team. In this blue box of informational alerts, essentially, the developers can get ahead of problems, like they can kind of see how their code is behaving and maybe head off at the pass an issue that later would have led to a severe alert in the middle, right? And the idea of being able to do these kind of smart alerts leads us to the topic of metrics anomalies. And so, first of all, what is an anomaly? This is the dictionary definition. And what's interesting about it is it doesn't actually say that it's bad, right? It just says something that is not normal. That's all an anomaly is. Sometimes it's bad, but not always. And why do we care about anomalies in our systems? Well, mostly it's because anomalies tell us sometimes when to act. We basically touch production for one of two reasons. Either because we're doing planned work, we're upgrading something, we're making something better in a planned way, or we're doing unplanned work to fix something. And it tends to be anomalies that notify us of that unplanned work that we need to do. And we're trying to minimize that unplanned work, right? Because anytime you touch production, there's some inherent risk there that something unexpected happens. So as much as possible, you want that to be planned. Now, we're going to look at a lot of different kinds of anomalies here. And there's lots of different anomalies that happen in the world. We're going to look at one particular category, which is metrics anomalies. And we've touched on this a bit already, but I'll reinforce that metrics anomalies are different from event anomalies. So most log systems are essentially event systems. And what is a log line or an event? It's an occurrence when something happened. It's time-stamped. It can have a lot of data associated with it, so it has arbitrary annotations. Duplicates can happen, and they're perfectly normal. Like the example below here is John Doe logged in, and he must have like clicked the login button twice, and we get 2 log lines here. That's fine. Most log systems would just log those 2 events as 2 separate lines. So the metaphor that we're working with here is a list metaphor. And you can see that there isn't actually any numbers in this case. Sometimes there are numbers in logs, but in this example there isn't. It's just this thing happened. No number associated with it. No concept of how many logins are going on. Metrics are actually a little different. I mean, they look similar in a lot of ways. They're also time-stamped. They also have arbitrary annotations, but they're not really a list, right? Like the log was just a list of things that happened. What a metric is a function that maps the value of the thing you're measuring to time. And it, like I said right at the beginning, Wavefront works with any numeric value that varies over time. In this case, duplicates actually don't make sense. Like you just have the number of logins that happened. Most metric systems will ignore duplicates. And this function metaphor then that we have with metrics instead of with log lines leads to 3 key advantages to using this kind of data for anomaly detection and alerting. The first is because these are numeric values, we have a whole lot of just mathematical machinery that we can bring to bear on top of these numbers. It's very easy to take all the numbers. I say easy, the Wavefront team here may not say it's that easy, but we did it, and pull them into a massive vector and store them and compress them extremely efficiently. And so that's why you can do things at the kind of speed and scale that I'm showing you in the demos, right? It's both cheaper to store that highly compressed numeric data than it is to store log data. And then because it's compressed, there's much less I/O to read it out, so you can do fast queries. And the final thing that's really important about this, and you'll notice like most log systems actually do this too, you can rely on human intuition. Now you have this functional machinery that you can apply to these numbers, and you can present it to humans who are good at looking for visual cues in data, and they can use their intuition to decide, is this thing really an anomaly or not? And I'll show one quick demo here. This is just a pure scale demo that kind of highlights what I'm talking about. Very simple data here. We're just looking at CPU load average across a couple of machines. What's interesting about this is that we're looking at data over a whole year, right? And if I take the average of this cluster, I just computed that in about a second. There's actually about 1 million data points that went into that calculation, and I'm able to crunch those 1 million data points in about a second and have the answer come back. Basically impossible to do this with log data, because in a log system, you'd have to parse all the log lines out over a whole year, basically convert them into metrics, and then do what we're doing. Another interesting thing is that this chart is actually kind of hiding something right now. So the Wavefront backend does not roll up or summarize any data, but the front end has to. There's more physical data points here than there are pixels on this projector. So I can't show every single physical point. But what I can do is ask Wavefront to show me when did this thing spike up. You see the average over a year was between like 1 and 8. If I say, show me when did this thing ever spike, I can see that in early April here, it actually spiked up pretty high, up to 90 or so, sort of 10 times different from the average. If I drill into that, I can see that that spike actually lasted for less than 10 minutes. So I was able to look at a year's worth of data, and if I pull the average off, we'll even see that it's just one of the machines in the cluster. So I'm able to look at a year's worth of data, see a spike that lasted for less than 10 minutes, and have that query come back in about a second, which is pretty cool. All right, so I'm going to show you a framework for thinking about and looking at anomalies. There's basically 2 ways that you can detect anomalies. And going back to the definition, an anomaly is something that is not normal. You can either define what the anomaly is directly, or you can just define what normal behavior is, and then your anomaly is when it's not that normal behavior. And in practice, the right-hand side is actually easier to do. I'm going to take you through 10 examples of anomalies. And there's actually going to be a shared theme to all of these. And that kind of the foundational idea of how to think about anomalies. And I'm going to highlight each of them with a red box. The first one is very obvious. This is just a range. This is a very traditional kind of threshold-based alert. Most of the time, this data varies between around 5 and 10, but it spikes up here to 30. Obvious. That's an anomaly, right? This is not so obvious, though. So there's some anomalies here, but they're not very easy to see, right? They're not spiking out very much. If I highlight, I can see here is one. So most of the time, this series is fairly flat. It spikes up for a few hours, and then it returns to normal again. That's an anomaly, but it's hard to see because it's not the biggest, it's not the lowest. But I can use Wavefront to pull the anomaly out. So here I'm showing how you could do this with interquartile range. You could also use standard deviation or other techniques. And what this is doing is measuring each new data point as it comes in and showing how different from recent past behavior that new measurement is. And when I do that, all the normal stuff drops off to 0 and the anomalies spike out. What about this one? So again, this one's not easy to spot either, right? We're looking at about 2 weeks worth of data. It spikes up and down all the time. Why is this highlighted one the anomaly compared to any of these other spikes and dips? Well, there's a seasonal ratio here. If I take every data point and compare it to what it was doing 1 week previously, I can see that most of the time, this thing is very stable. It only differs between 1 and 1.1. But that spike that was down in the chart is very different to what it did last week. So the seasonal ratio here is making that anomaly pop out. Here I've just actually used 1 week, but it's easy to use Wavefront to calculate what's normal from multiple weeks worth of data and then alert when you deviate from that normal behavior. Another tricky one here, right? So there's an anomaly here, but it's very hard to spot. This is data that these are both counters, right? If you look at it, it's actually going over several weeks worth of data, and it's just counting something. This could be total number of packets sent on 2 network interfaces, for instance. And just each time a new packet gets sent, that number just goes up and up and up. We can't really see anything weird here, but oftentimes if you're measuring something that's increasing, you might want to know how fast is it increasing? How much is that number changing every second? And that's the rate. Just very easy to look at the rate of that. And when we rate those two things, now again the anomaly leaps out. One of them actually spiked up for a little bit and returned to normal, whereas one of those lines was actually was increasing unusually slowly for like 3 days. Okay? This is an example of a serial pipeline. This is something common in our customers. So a lot of our customers will use something like Kafka to store all their metrics. They have various stages of their pipeline through which data goes. And what we're seeing here is the final stage of that pipeline is dropping really low. And this might be actually causing queuing or drop points or something like that. And it's a little, this does look weird already. Some of the examples I showed, you can't see anything weird initially. This one, it does look odd, right? And a great way to think about alerting over this would be the group range. Just the maximum value minus the minimum value. Most of the time, so what we're expecting as normal is a very low group range, but when it spikes high, we know we have an anomaly. This is a parallel balancer. So previous was a serial thing, here's a parallel one. So this is just like a typical load balancer. F5, ELB in Amazon, Nginx, HA proxy. And you can see that these things are starting to deviate from one another, right? And this is probably a bad thing. Like probably one part of this pipeline is overutilized while other pieces are underutilized. So you probably want to know about this, or at least someone in the organization does. And here, a good way to detect it is looking at the group variance. And here, actually, we're looking at the standard deviation here, so the square root of the variance. And again, you can see when it started to go odd very clearly on this chart now, right? Coming back to the idea of, not having every alert go to every team, is the team downstream of that might not have considered that previous issue an anomaly at all. They may not care, right? All they care about is, are they getting their data? And if you sum this up, the pipeline was processing all the data the whole time. The downstream team doesn't care. So again, you want alerts going to appropriate teams who care about that problem and can investigate it. Here's an interesting one, right? So this is just looking at CPU. And why is this one an anomaly? It's not the highest number. It's, again, super spiky data here. This is not the highest number. There's a higher number on the right-hand side. It's very easy to see why this one is anomalous if you compare this to a demand metric. So if I overlay requests against the CPU, we can see that normally requests are very well correlated to CPU. Request rate increases, CPU increases. But for some reason on this Saturday, the request rate stayed low, which is typical for a Saturday, but the CPU went up. And so if I just compare one metric over the other, I can see when it goes bad. Normally this stays around 1, so very correlated. But when the bad thing happened, it spiked up higher. Okay? And that goes back to simple alerts tend to look at just one thing. But in order to do smart alerting, you often have to combine different metrics together to know what's really going on. What's going on this one, right? So we have two things here. They have, if you look at the left-hand side of the chart, they seem to be completely independent of one another. They're just changing and spiking on their own. But on the right-hand side, they almost look to be inversely correlated to one another. One of them spikes up, the blue one spikes up, the green one spikes down. This is a telltale sign of something fairly common. These two things are consumers of a shared resource. Could be CPU, could be storage, could be another service. And what this is indicating is that that shared resource is probably pegged. So normally, these things are fairly independent from one another. They ask for the resource, they get it. But when that resource gets pegged, when one gets it, the other can't, and so it drops. And we actually can correlate that data directly in Wavefront. This is a function that will actually correlate one data point to another, or one data point to many other data points. And the function would return 1 for this data is totally correlated, 0 for this data is not correlated, and -1 for this data is completely inversely correlated. And you can see here that normally it varies between -0.5 and 0.5, fairly uncorrelated. But then when the resource got pegged, it reached -1, very correlated, very inversely correlated. Final example, missing data. This is something that most of our customers have faced. If you're measuring hundreds of thousands of things per second, it's kind of a fact of life that eventually you will have some missing data. And an easy way to detect that is to just count how fast the data is coming in. This function is saying how many data points did we get in a 20-minute window. And we can see that in that 20-minute window we got none, and we can alert over that. This thing is so common that in the version of Wavefront that we've launched here at VMworld, Wavefront alerts will actually detect this for you automatically. You don't even have to write any query like that. If you have any alerts and there's missing data for those alerts, you'll know about it without you having to do anything. And then I said there'd be 10 examples, but of course an 11th one is you can use any of these techniques and combine them together. And some of our customers have, these are examples of real alerts, and some of our customers have got some very interesting, very customized alerting, very specific to their environments that they know intimately, right? And I said at the beginning, there's a shared theme here. These are all the kinds of anomalies that we just looked at. But actually, one of these is sort of more important than the others. And it's actually that first one, that range. Everything else, all I did was take the behavioral difference that a human can't really see and converted that behavioral difference to a range. And then when you have the range, it's very easy to alert over. Let's quickly just go through. So behavioral difference converted to a range. Now I can alert over this when this goes above a certain number of interquartile range. Behavioral difference converted to a range. It leaps out. Behavioral difference, range, behavioral difference, range, behavioral difference, range, and so on and so forth. So the trick to alerting is to take your data, convert it using the kind of techniques that I've shown here into a range, and then you can very easily just alert when you go beyond an acceptable threshold in that range, right? And why? Why is it this way? Why is this the way that we recommend looking at alerts? It basically comes down to us, right? We're kind of hardwired to think about ranges. There's some pictures here of penguins and birds. Everyone's looking at the same penguin right now. In fact, in the picture of the owls, even the owls are looking at the same one. It's the biggest one, right? That's just how we're hardwired to look at these things. We're not hardwired to observe behavioral differences. If I show you 1,000 lines, these are the data points for 1,000 different things, you can't see which ones are reporting less frequently than others. But we're just not attuned to seeing behavioral differences, but we are attuned to seeing ranges. And then finally, what happens next, right? You get alerted, you know that you have a problem. How do you diagnose that problem? I'll show a very interesting little demo for that. So this again is an example from a real customer, a support ticket that came in. Again, it's kind of not exactly the same data, but very similar. And the issue here was in the network. So we call this the needle in the haystack example. We're looking at a whole bunch of noisy network data. The customer actually knew from their customers that they had an issue around the middle of this chart, but they had no idea what's going on. And they wanted to figure it out fast because they were worried about it happening again. One of their network engineers found one of the switches that was behaving abnormally. So they knew they had an issue around the middle of the chart. They looked at some of their core switches, and they saw one that leapt up in the middle of the chart. This seems like a part of the problem. But if only this switch was going haywire, the whole network would probably be fine. This is when they grabbed the link to the data, they sent it to Wavefront for help. These links are really useful inside your company, but they're really useful for getting help from us too, because we can see what you're looking at right away. And they actually reached out and said, hey, I'm going to manually compare this switch against all the other switches and look for ones that seem similar. Is there anything better? And we said, yeah, Wavefront can actually do that for you in like a second. So this query is correlating the original needle, that one problematic switch, to all of the other switches in the haystack, and only displaying those that are very highly correlated. You can see that this even doesn't really care about the scale of the data. Like this green one is much lower magnitude than the original, but it does have a very similar shape. It turned out when they looked at all of these that they were all from the same switch manufacturer. So the customer had a whole bunch of different switch vendors. These were all one vendor. They all had a bad firmware that needed upgraded. And they told us that this saved them hours of painful manual investigation to figure out what was going on. So might have time for one or two questions. I'll direct you again at our new trial. Go to wavefront.com. There's lots of good resources there, and just click Get Started at the top, and you can get a trial of this and try some of this for yourself. There's a bunch of other sessions going on. The one I'll highlight actually is tomorrow at 12:30 in this same room. One of our customers, Box, is going to be presenting their use of Wavefront and some of the interesting things that they've discovered using our tool. Thank you.